Hello everyone. In this video, I am explaining about singular and non-singular linear transformations. Suppose you have a linear transformation T from V to U. Two vector spaces V and U are the two vector spaces over a field R, and T is a linear transformation from V to U. Now, we say this linear transformation as a non-singular linear transformation if only 0 vector of V maps to 0 vector of U. No other vector maps to 0 vector of U. So, only 0 vector of V maps to 0 vector of U. That means 0 vector is the only vector whose image under T is 0. Okay, 0 vector is the only vector whose image under T is 0. No other vectors are mapping to 0 vector. That means what happens to the kernel? That is where the significance of kernel comes here. So V to U, T is a transformation. Now, if kernel of T means only 0 of this vector space maps to 0 of the next vector space, then such transformations are called as non-singular. Means kernel of T contains only one vector, which is the 0 vector. Kernel of T equal to set containing 0. In this case, your transformation T is non-singular. If the transformation T is singular, then there exists at least one non-zero vector V not equal to 0 in V such that T of V equal to 0. You know that under a linear transformation T of 0 is always 0. Okay, 0 vector maps to 0 vector of other vector space. Suppose if you have a non-zero vector of V which maps to 0, then such transformation becomes singular. Means kernel of T is not equal to only set containing 0. Then your transformation T is singular transformation. So this is the meaning of singular and non-singular transformation. Non-singular means only 0 vector maps to 0 vector, means kernel of T equal to set containing 0. If kernel of T is not equal to set containing only 0, then in such cases T is a singular transformation. Let us take one example. So we had the transformation from R square to R square, rotating a plane by 90 degree clockwise. It is given as y comma minus x. So in this case, T of x comma y equal to 0 comma 0. Let us find out the kernel of this transformation. So kernel means you have to find out which vectors map to 0 comma 0. T of x comma y is nothing, y comma minus x, which is equal to 0 comma 0. This implies y equal to 0, x equal to 0. Therefore, only 0 vector maps to 0 comma 0. So what is kernel of T? Kernel of T equal to set containing only 0. So what kind of transformation this is? T is a non-singular transformation. Therefore, to check whether the given transformation is singular or non-singular, always find out the kernel. If kernel comes out to be only 0 vector, then it is non-singular, otherwise it is singular. See one more example. Take transformation T from R cube to R cube, the projection map T of x comma y comma z equal to x comma y comma 0. So this is that projection map. So in this case, let us find out the kernel, which we already did in our previous videos. Kernel of T is equal to, you have to find out all those vectors from R cube. So x comma y comma z belongs to R cube such that T of x comma y comma z equal to 0. Which are the vectors? They get mapped to 0. Means T of x comma y comma z equal to 0 comma 0 comma 0. Means x comma y comma 0 equal to 0 comma 0 comma 0. So this implies x equal to y equal to 0. This is the equation of z-axis. So entire z-axis gets mapped to 0. Therefore 0 comma 0 comma z where z belongs to this is the kernel. Now kernel of T is not just the set containing 0. This is not equal to only set containing 0. Okay, therefore your transformation T is a singular transformation. Singular because there are other vectors which map to 0 other than 0 vector, because you know that 0 vector always maps to 0. Other than this 0 vector, there is this vector 0, 0, 1, where it goes to after applying the transformation 0, 0, 0. See, 0, 0, 1 goes to 0, 0, 0. Similar 0, 0, 2 goes to 0, 0, 3 goes to entire z axis goes to the origin 0 of the other vector space. Hence, the kernel of T is not equal to set containing only 0. Hence, the transformation is a singular transformation. So this is where the significance of kernel of T comes. If you know what kernel of T is, then you can say whether the transformation is singular or not. If kernel of T equal to set containing only the 0 vector, then that transformation T is non-singular. So which implies again that transformation T is 1 to 1. The given transformation T is 1 to 1 if kernel of T is equal to only set containing 0. So if and only if also you can add. If T is 1 to 1, then kernel of T is equal to only set containing 0. Hence the transformation T is non-singular. Similarly, if T is non-singular, then kernel of T equal to set containing 0. Hence, T is 1 to 1 mapping. So, the first case here, this mapping, rotation of a plane by 90 degree clockwise, this is non-singular as well as 1 to 1. 1 to 1. This mapping is 1 to 1. Now, one more thing to remember is this kind of transformation. Non-singular transformations take linearly independent sets to linearly independent sets. Means if you have a transformation T from V to U, this is non-singular. So in that case, suppose you have a linearly independent set in V. So after taking the transformation, this goes to a new set, correct? No, in the other vector space. That set is also linearly independent. That is the property of non-singular transformations. Now let us take a few more examples to identify whether the given transformation is singular or not. So in that examples only I will illustrate this, how linearly independent set goes to linearly independent set in a non-singular transformation. Let us solve some problems. See, the first problem is you have to find out whether the given transformation is singular or non-singular. F is a transformation from R square to R square. This is a linear transformation given by f of x comma y equal to x minus y and x minus 2y. So remember to check, is it singular or non-singular. Always find out kernel of the transformation. If it is equal to set containing only 0, then it is non-singular. Otherwise it is singular. So how to find out the kernel of this transformation? So f of x comma y must be mapped to 0 comma 0. Okay, so this implies x minus y, x minus 2y equal to 0 comma 0. So this implies x minus y equal to 0, x minus 2y equal to 0. You got a set of simultaneous equations. So you can write it how to solve. This is a system Ax equal to 0, homogeneous system in two variables. How to solve this homogeneous system? You can do that directly, just two equation, or else usual procedure 1 minus 1, write the coefficient matrix 1 minus 2. This is the coefficient matrix. Reduce it to echelon form 1 minus 1, R2 minus R1, 1 minus 1 0, minus 2 plus 1 minus 1. Okay, so this is the echelon form of the matrix A, coefficient matrix A. Find out rank of this coefficient matrix equal to 2 number of non-zero rows you have to count. These two are non-zero rows, which is equal to number of variables. Okay, this is equal number of variables. How many variables here? You have two variables. You know that the homogeneous system Ax equal to 0. I had made a separate video on how to solve a homogeneous system. You can watch that video to understand how to do that. Ax equal to 0 has a non-trivial solution if rank of A is less than number of variables. N means number of variables. In case if this happens, then only it has non-trivial solution. Non-trivial solution means other than 0 solution, because 0 is always a solution of this system. Okay, now in this case you got it equal to number of variables. It should be less than number of variables to have non-trivial solution. Therefore, only trivial solution exists for this system. Trivial solution exists. What is the trivial solution? 0 solution. So, what is now kernel of T? 0, 0. Only 0, 0 vector maps to 0, 0. Hence, what kind of transformation this is? This is non-singular transformation. So, this is how to find out whether the given transformation is non-singular or singular. One more example, let me give you. One more. A mapping, linear mapping G from R square to R square given by G of x comma y equal to 2x minus 4y comma 3x minus 6y. So you have to check, is this transformation T, is this transformation G singular or not. So how to do that? First find out kernel of T. So how to find kernel of T? First equate this mapping to 0, 0. So this gives you 2x minus 4y, 3x minus 6y. This is equal to 0, 0. So this implies 2x minus 4y equal to 0, 3x minus 6y equal to 0. Again, homogeneous system of equations. Write the coefficient matrix 2 minus 4 and 3 minus 6. So you can divide the first equation, first row by 2 and second row by 3. So R1 by 2 and R2 by 3. So in that case you will get 1 minus 2. This is also 1 minus 2. Then you can do R2 changes to R2 minus R1. 0, 0 you will get. So what is this rank of this matrix? Rank of A equal to number of non-zero rows 1, which is less than the number of variables, because there are two variables x and y, number of variables. So if rank of A is less than the number of variables, there exists non-trivial solution. Now you don't want what are those non-trivial solutions. Just we want to check, is kernel of T equal to only set containing 0. In this case it is not equal to kernel of T, in the sense here kernel of G is not equal to set containing only 0. Hence the given transformation is singular transformation. This is singular transformation. Okay, because we don't want actual solutions here. We want to check, is only 0 vector getting mapped to 0. Here no, not just 0 vector mapping to 0. There are other non-zero vectors which are mapping to 0. Hence the transformation becomes singular. Now take up one more example. G from R square to R cube, such that G of x comma y equal to x plus y, then x minus 2y, then 3x plus y. 3x plus y. So you have to check, is this transformation singular or not. So G of x comma y equal to 0, 0, 0. This is the 0 of R cube. Just check what is the 0 vector of the second vector space. So this is x plus y equal to 0, x minus 2y equal to 0, then 3x plus y equal to 0. So you got here 3 equations in 2 variables. So you have the coefficient or matrix of this system 1 minus 2, 3 and 1. So this gives you 1 1. R2 changes to R2 minus R1. R3 changes to R3 minus R3 R1. So do that. 1 minus 1 0, minus 2 minus 1 minus 3, then 3 minus 3 0, 1 minus 3 minus 2. Okay. Now so this can be simplified further as 1 1 0 minus 3, and here this is 0 0. to apply the operation, R3 changes to R3 minus 2 by 3 into R2. So that 3 cancels, minus of minus plus minus 2 plus 2 becomes 0. So what is rank of this matrix? Equal to 2. Number of variables is also equal to 2. Number of variables, that is equal to number of variables. Hence, do you have non-trivial solution? So no non-trivial solution for this. Hence, what is the kernel? Kernel is only the trivial solution. So kernel of T is equal to only set containing 0, 0. Therefore, this transformation is non-singular. No non-zero vector goes to 0 of the vector space R cube. Hence, this transformation is kernel of T, means here kernel of G. So kernel of G, we will get it as only set containing 0, 0, 0 vector. Hence, the transformation is non-singular. Therefore, that means only 0 vector maps to 0 vector. Now see here, we found this transformation is a singular transformation, means other than 0 vector, other non-zero vectors also map to 0 vector. So hence this transformation was singular. And I told you the characteristic property of non-singular transformations is that it takes linearly independent sets to linearly independent sets. After taking the transformation under non-singular transformation, linearly independent set goes to linear independent set. So under singular transformation, that won't be true. Let us check how. You know that 1 0 and 0 1, this is linearly independent set of R square. Now take the transformation, that is g of 1 0 and g of 0, 1, where it goes to g of 1 0. Put x equal to 1, y equal to 0. This goes to 2 and 3, not minus 3. So it is 2 and 3. And here this comes g of 0, 1. Put x equal to 0, y equal to 1, so minus 4, minus 6. Now you got a new set. After taking the transformation, this set goes to this set. Is it linearly independent? This is not linearly independent, because this vector is a multiple of this vector, minus 2 times 2, 3. So if you have two vectors, if one vector is a multiple of another vector, then that set cannot be a linearly independent set. So this is not happening here because the transformation is singular. Under singular transformation, linearly independent set need not map to linearly independent set. But under non-singular transformations, see, this is non-singular transformation, linearly independent set goes to linearly independent set. See, for example, take 1 0 0 1. This is linearly independent set of R square. Okay. After taking the transformation, that is f of 1 0 and f of 0, 1, where it goes to f of 1 0 goes to 1, 1, and f of 0 1 goes to minus 1, minus 2. So you got a new set. Clearly this set is linearly independent because they are not multiples of each other. Hence, this transformation was non-singular. Non-singular transformation take linearly independent set to linearly independent set. Under singular transformation, that need not be true. Hope you understood the concept. Thank you for watching.